All right, so chapter 10, section 1. This is a lot of vocab. And then it gets into a couple of theorems. We're going to do this between today and tomorrow. So the homework today will cover what we cover up till the end of today, and then tomorrow we'll continue. But it is all the start of circles. So a circle, by definition, is the set of all points in a plane that are equidistant from a given point in that plane. So if I had a point and then I went out the same distance in all directions, and then I connected all of those, that's where the circle comes from. Okay, so that's the definition. Equidistant from the same point. If you took a point, you drew, like you connected a little string to a pencil and you went the same direction in all, the same distance out in all directions, that's what the definition of the circle is. That given point in the middle of that circle is the center. And the radius is the segment whose endpoints are the center and any point on the circle. The plural of radius, so more than one radius, is called would be called radii. So radii is the plural of radius. Okay, a chord is a segment whose endpoints are on the circle. Nope, it would be on a circle. So the radius is going to go from the center, right, to the side. That would be the radius. A chord has two endpoints on the circle. So just a segment that would connect those. Side to side. A diameter is a chord that contains the center of the circle. So if I were to take that chord which goes end to end and I pass it through the center of the circle, that's a diameter. So by definition, a diameter is a chord. But if you were looking at a diameter and it asked you to name it, the better name would be the chord. A diameter, sorry. On the next slide, you're going to see all these pictures too. So that's a diameter. The secant is a line that intersects a circle in 2 points. So a secant actually passes through the circle. If I extend a diameter past the edges of the circle, it would be a secant. But it actually could be any line that passes through the circle. It hits the 2 sides of the circle. That would be a secant. And a tangent is a line in the plane of a circle that intersects the circle exactly 1 point, called the point of tangency. So a tangent bumps up against the circle, but does not cross into the circle. So it hits against 1 point of it is going to overlap on the edge of that circle. And that point is called the point of tangency. So in the beginning of this chapter, you're literally going to have to identify from a diagram which of these they are. It could say which one's a secant, or it could say name a secant. And then obviously this terminology starts to get built into theorems and postulates. All right, so here's your visual. The top one is a chord. It goes from end to end, so both end points are actually on the circle. The diameter passes through, so if the center was here, the diameter would pass through the center and have both endpoints on the circle. A secant goes beyond the edges of the circle, and it's a line. And the tangent just hits 1 point on the edge of the circle. It's also a line. So tangents and secants are lines. They do not end. And then what's not on here would be a radius. So half this diameter would be the radius in either direction. End point on the circle, the center, and the actual circle. And this is the point of tangency. All right, so example 1 says point O is the center of the circle. Name each figure. The first one is OM. OM would be a radius. Good. The second one is MN.
Okay, why are there like two MNs? Like
One goes through.
Because one is a segment, so it stops at the endpoints. Good question. This is segment MN, which means it stops at the endpoints, which makes that a what? A chord. The next one has arrows, so it's saying go beyond this in both directions, which would make it a what? Good. Then you've got MQ. Good. It's a chord and a diameter, but better described as a diameter. Good. ML. Where is ML? So it's a tangent, but it's got endpoints. This is a trick question because we haven't talked about it yet. But this is called a tangent segment because it ends.
I'm gonna have to know this for the quiz.
You're going to need to be able to identify them. Yeah.
Tangent segment?
Tangent segment. So if it ends, but it doesn't pass through the circle, if it only touches the circle at one point, then it's a tangent segment. If it has arrows, now it's just a regular tangent. So the tangent is a line. And point M is called? Good. Questions on those? All right, common internal versus common external tangent lines. So a common tangent would be a line that is tangent to two circles, okay? In the diagram that you're looking at, I know one crosses kind of into it, but it's nearly impossible to get it to there. But let's just pretend it's touching these 2 points. That line would be tangent to both those circles, so it's called a common tangent. And the same on the right. This is common. It's a common tangent because it touches both those circles. But within common tangents, you want to classify them as internal and external. And the way we do that is by drawing a segment connecting the centers of the circles. So if I had this circle here, obviously, and this circle here, and I drew a segment that connected them, it would look like that. If the common tangent crosses through that segment, then it's an internal tangent. If it doesn't, it's an external tangent. So if I do the same thing over here on the right, I draw the two centers, and then I draw a segment that connects it. Looking at the diagram on the left, does the segment I drew intersect with the common tangent?
Yes.
The one on the left, right? This one, does this intersect this? No. So this would be a common external.
I think of it just like the line is in the inside.
Sure, it doesn't pass through the middle of them. That's fine.
And then like the other side, like the line goes on.
It literally goes in between them, right? So this would be a common internal tangent. So does it intersect the line you drew? No, it's external. Yes, it's internal. All right, congruent and concentric circles. Congruent circles are circles that have congruent radii. They don't have to be the same circle. Like obviously if one overlaps the other, then it would be the same circle. Those would be congruent as well. But all you have to have is the same radii. So if I have two circles with a radius of 5, they are congruent circles. Concentric circles are ones that lie in the same plane and have the same center. So these look like a dartboard or a bullseye. Those would be called concentric circles. They have the same center, obviously different radii here, but the same center. So this is concentric circles. Because congruent means same size and shape, right? This says shape, they are both circles. Size means they'd have the same radii, which means they'd have the same diameter, because you would just double it. All right, and then tangent circles are coplanar circles that are tangent to the same line at the same point. So they don't have to overlap like the ones on the right. They could be next to each other. The rule is that whatever line that is that's tangent to both, the point of tangency would have to be the same for both circles. So the ones on the left are tangent circles, and so are the ones on the right. Even though it lies within it, they both have the same point of tangency on that line. All right, first theorem of the chapter. So theorem 10.1 says, in a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the point of the circle at the point of tangency. So the line has to be tangent to the circle at the point of tangency and then intersect the radius. And when it does, it's perpendicular, which means there'd be a right angle on either sides of that radius. And because it says if and only if, it means this is true for the original statement and its converse. So its converse would say if the radius is perpendicular to a line then, well, a line outside the circle, not one inside, because that could be a chord, then the line is tangent to the circle. So I can use this in two ways. I can use this to find the length of one of those segments by using right triangles, or I can use it to prove BC is tangent to the circle.
Will circles ever have sine?
They could.
Great question.
Yeah, not like if you wanted to find the length somewhere, it could give you, but we'll get to angles later. But it will give you like an angle on the inside, and it could be an angle like 42 degrees, and you've got to find the length. Yeah, but we're not anywhere there yet. Yeah. Okay, we're going to come back to this tomorrow. All right, theorem 10.2. So the first theorem says that the tangent would be perpendicular to the radius. The second theorem is the tangent segments from a common external point are congruent. We refer to this as the ice cream cone because that's what it looks like, okay? So if you have two tangent segments, they have to be segments, otherwise they don't end, so we can't measure them. Two tangent segments that come from the same external point, then those segments are congruent. So if I have the side length of one, I set it equal to the other and solve. That's as easy as it is, okay? But these are the ones that are going to have x squareds, so this is why we review how to solve quadratics, because you might have to factor these. You might have to use the quadratic formula on these, okay? But sometimes you'll see the squares on these. So we're going to go to example 2. So in this circle, first of all, I know it's a circle. R would be the center of the circle. It will usually have a little dot like that, okay? And OT is tangent to the circle. So if that's the case, if OT intersects the radius, then it is perpendicular to the radius, which means it's the right angle there. So if A says if OR is 6 and OT is 8, then find RT. What do I know about that triangle? It's a right triangle. I can use Pythagorean theorem, which would say 6 squared plus 8 squared would equal RT squared. Or 36 plus 64, 100 equals RT squared, and RT is the square root of 100, which is normally plus and minus 100, but because we're talking side length, it's only the positive, which is 10. That is also a triple 6, 8, 10. Know it, and it saved you all that work. Yep. So remember your triples: 3, 4, 5, 6, 8, 10, 5, 12, 13, 7, 24, 25, 8, 15, 17. Okay. Those are going to pop up still because we're still dealing with right triangles. Questions on that one? Okay, B says if the measure of angle OTR, which is this angle out here, is 45 degrees, and OT is 4, then find RT. Now what kind of triangle do I have? Isosceles right, which is also 45, 45, 90. The relationship of the side lengths on a 45, 45, 90 triangle are opposite the 45 would be the A's, and opposite the 90 would be A root 2. So if 4 equals A, then RT equals 4 square root 2. We're going to go to example 2. So in this circle, first of all, I know it's a circle. R would be the center of the circle. It will usually have a little dot like that, okay? And OT is tangent to the circle. So if that's the case, if OT intersects the radius, then it is perpendicular to the radius, which means it's the right angle there. So if A says if OR is 6 and OT is 8, then find RT. What do I know about that triangle? It's a right triangle. I can use Pythagorean theorem, which would say 6 squared plus 8 squared would equal RT squared. Or 36 plus 64, 100 equals RT squared, and RT is the square root of 100, which is normally plus and minus 100, but because we're talking side length, it's only the positive, which is 10. That is also a triple 6, 8, 10. Know it, and it saved you all that work. Yep. So remember your triples: 3, 4, 5, 6, 8, 10. 5, 12, 13, 7, 24, 25, 8, 15, 17. Okay. Those are going to pop up still because we're still dealing with right triangles. Questions on that one? All right, example 3 says name a line tangent to circle P but not circle O. So looking at this diagram, I want something that intersects circle P at one point, but does not do the same to circle O. What is that? CP, I could call it CP, yep. So CP would be tangent to circle O and cross through circle P. So that's why I know it's not the same thing. So CP, and it says a line, so it would be line CP. B says name the common external tangent to circle O and circle P. So what segment is tangent to both but doesn't cross through the in between them? CD. And again, it's a tangent, so it's line CD. Or DC, it could be either one. And C says name the common internal tangent, which would be what? What line is tangent to both but does cross through in between them? AD. If you don't see it, then draw yourself the segment that connects the two circles. Okay, the common tangent was CD and it didn't intersect that pink line. The other common tangent is AD and it did intersect that line. So that's the difference between it being external and internal. Questions on that one? Yep.
For the first one, what's the line tangent to circle P but not circle O?
Oh, that's the other way around.
Yeah.
Sorry. You're right. So that would be the other way. That would be tangent to circle O and not circle P. So the one that is tangent to circle P and not circle O is which one? So that one is tangent to circle P, but not circle O. Thank you for catching that. Questions? All right, so it's important to read the instructions on these because before you start to make assumptions, sometimes they will be labeled and sometimes they will not. If there's a solid dot in the center of the circle, that means that is the center. If it's not, it could just be a point somewhere in the circle. So there will be eventually like these floating points. So you want to be careful, okay? For the most part now, it will be in the name. Like it will say circle M, and that means that M is the center of that smaller circle. And it says circle N, and it means it's the center of that bigger circle. But as we start to build on these, we're going to learn some more theorems and postulates and stuff that are things that happen inside that circle. It's important to make sure you're paying attention to, is it the center or not, okay? If it's not the center, then a segment that connects it is not the radius. So things like that you want to pay attention to. Then it says PR and SR tangents to the circle. So I know that these two that forms that like ice cream cone shaped, those are tangents, which would mean they were equidistant from the endpoint on the outside. And then circle N has a diameter of 16, PQ is 3, and RQ is 12. So if I just label what they gave me, that's already labeled, or that's already named, would be PQ is 3 and RQ is 12. And then it says that the diameter is 16, okay? So straight across my circle through, through the center would be a diameter. So it could literally be drawn this way. That could be a diameter. It could be drawn this way. That could be a diameter, like all the way through my circle. And you could use it in any direction you wanted to, okay? So if I were to, let me group it. If that whole diameter is 12, what does that tell you about the part of that diameter that's inside the smaller circle? So if that whole thing is 12, what's that tell you about N to P? From the center to the other side of the circle. If my diameter is 16, not 12, sorry. The diameter is 16. So yes, this segment here would be 8. So I know based on that, which one is NP? Oh, it's not on there. Okay. I have to find PM, which would be half that 8, right? That's going to be 4. I have to find MQ. So if I have this diagram in here that I could fill in as a right triangle, this 4 was half of the big diameter, right? Which is the radius of the small circle. And then I've got 3 for PQ, which tells you MQ is what? This is a small right triangle, right? One side is 4, one side is 3, which tells you what's the hypotenuse? 5. PR is this whole thing. That one's easy. I could just add the 3 and the 12. That's 15. SR is this side, which, what do we know about those two tangents? Good. So this would also be 15. NS is the radius of the big triangle, which would be what? 8, half the 16 that they gave you. And NR is a segment that wasn't drawn yet. I have to draw it in. Now, if I make it, and you can make it in either direction, it can either be a right triangle here, or it could be a right triangle on the right, which is a little bit less crowded. So let's say we use that one, okay? I know the radius here is 8. I know SR is 15, which tells you NR, which would be the hypotenuse of that triangle, is what? What's the triple with 8 and 15? 17. So there's a lot of overlap here. You've got your new theorems that are like the ice cream cone one. The tangent's going to be a right angle. And then you've also got your Pythagorean theorem coming back. You've got your 30, 60, 90, 45. 45, 90 can come back. And you've got your Pythagorean triples, okay?
Basically, it's not a circle chapter, it's a triangle chapter.
It's a circle. Yeah, it's triangles within the circle. So it's going to be both. It's going to be both. Yeah, Jonathan. Say again?
They got B.
What? No. How did I get what?
B and
B and F?
Yeah.
Okay. B is MQ. So MQ, let me clean this up.
As you can see.
Okay. MQ is here. Writing there, right? So MQ makes a little right triangle here. It's tangent, so I know it's a right angle. The 3 was what they gave me. PQ was 3. But then the MP is the radius of the small circle. If the whole circle diameter is 16, right? Then that means that N to P is 8, and then M to P is 4. And then it's a 3, 4, 5, right? And then F, I use the other triangle. So N, R, S. RS is 15, NS is 8, and it's a right triangle. That missing triple side is 17. If you don't remember your triple, you got to use Pythagorean theorem.